Yeah, hi. So this session, I'm going to talk about vehicle routing. So vehicle routing is was one subpart of our problem, which we were doing for clients. So the other part was bin packing. So in this short video, I will be covering only the vehicle routing part. Okay, yeah, so first, in order to understand about vehicle routing, I will first go through some basics. What is what is vehicle routing, and like why do we even need that, and how it is applied in the business, stuff like that. Okay, so uh, for first, I will try to introduce you to the operation research. So, operation research is an analytical approach to solve business problems. So, the key aspects include given one business problem, first, usually it involves trying to optimize a certain objective. And optimizing the objective involves either maximizing something or minimizing something. And then it involves some constraints. Usually, the real world problems contain some constraints because we need to act within those constraints. So next step is like we need to figure out what the constraints are. And the third step involves the decision variables. The decision variables are the variables which are under our hand, which we want to uh, which we want to use for optimizing our goal. So these three things we need to figure out. And the operation research involves figuring out these three things and then converting this into a mathematical model. So next thing is like once we have converted something into a mathematical model, we need to solve it. In order to solve it, there are various methods, techniques, and stuff. But in order to understand these techniques and why we have to apply these techniques, first I will introduce you to the fundamental concepts of a computer of a computationally solving a problem. So the first thing is algorithm. So an algorithm is a step-by-step procedure for solving a problem. And the second thing is a Turing machine. The Turing machine is a abstract machine. So basically, it involves manipulating the strip, an infinite strip, according to some table of rules. And polynomial time. So an algorithm runs in a polynomial time if we can upper bound the uh, running time by a polynomial expression. And then deterministic versus non-deterministic. An algorithm deterministic if at each step the machine over here is the Turing machine has only one possible action. And it is non-deterministic if a machine can take uh, multiple possible actions. So ideally, it's a probabilistic way, like 80% of taking action A, 10% of taking an action B, 10% of taking an action C, stuff like that. So these are the fundamental concepts. And then based on the running time, the complexity of the algorithm, we can divide the algorithm into two. The complexity of the algorithm into two types: the polynomial time algorithms and uh, non-deterministic polynomial time algorithm. So in a polynomial time algorithm, the problem can be solved in a polynomial time by a deterministic Turing machine, meaning that the running time of an algorithm can always be upper bounded by a polynomial expression. And examples include sorting a list of numbers, finding the shortest path in a graph. Here, it's only the shortest path between any two nodes in a graph. And for a non-deterministic problem, these problems cannot be solved in a polynomial time, but they can be verified. If someone gives us a solution, the solution can be verified in a polynomial time. And examples include Boolean satisfiability problem, traveling salesman problem. So SAT is nothing but someone just gives you a Boolean formula and asks you to figure out all the variables that satisfy this formula. It can't be done because there are so many multiple combinations that will satisfy. Permutation is a combination that will satisfy. But if someone gives you the variables and asks you to check if it can be satisfied, then it can be easily done. Similarly, for the traveling salesman problem in a very small situation can be actually be converted into a polynomial time problem, but at a large scale, it's a non-deterministic. So, in generally, traveling salesman, it's like considered non-deterministic. So, for people who don't know what a traveling salesman is, traveling salesman problem is like you have like set of cities, and a salesperson or a salesman has to just go through all the cities without crossing the already visited cities again. So he has to visit each cities, and each cities has to be visited uniquely, and he has to do it in the shortest route as possible. That's a simple traveling salesman problem. And then now we know like we have some business problem in the operation, and we need to apply the operations research, and we to solve it. So in order to, and we know that there are like certain problems that can be solved in polynomial time, and certain problems that can be solved in a non-deterministic polynomial time. So now, how do we know the algorithm? Now we know how we know the complexities. We know how to do it, but like how do you actually how do you actually solve the problem? And how do you actually solve the problem, or these techniques that are presented here? So the first thing is linear programming. So when we are talking about the constraints in slide one, if those constraints can be formulated as a linear constraints. For example, x plus y is equal to 2, it's a linear. But x square is equal to 3, or x cube is equal to 8. So these are non-linear constraints. So when the constraints are linear, then we can apply something called as linear programming to solve it. So here both the objective and the constraint should be linear. And simplex is one of the methods that is used for solving this linear programming problem. And the second thing is integer programming. So integer programming is used when all the variables or all the decision variables in our problems are integers. So for example, it can be binary choices, 0 and 1. Whether we need to, for in the case of a traveling salesman problem, whether we need to visit the city or not next. That can be answered in a 0, 1. You can visit the city as 1, you cannot visit the city as 0. So when we convert all our variables to integers and use it in our problem solving, then it becomes an integer programming. And in integer programming also, integer programming can be solved by simplex method, but solving by simplex method will give you a floating value answer. So once you get the floating value answer, you apply a branch and bound technique to further solve it. So I'm not going to go through the simplex method, branch and bound technique, stuff like that, because that will take a lot of time. But these are just the ways in which you can uh, convert a business problem to an optimization problem and apply optimization techniques to solve it. The third thing is the network optimization. So the network optimization deals with problems represented as a graphs or networks. For example, the traveling salesman problem can be converted into a graph problem, or the shortest path in a graph problem can be and minimum spanning tree problems. So these sort of problems, we make use of network optimization framework to solve it. The fourth one is the dynamic programming. So dynamic programming basically involves breaking a complex problem into various subproblems and solve each subproblem and combine its solution to solve the bigger one. And these are like, and again, these can be applied to even the shortest path or resource allocation problems. So for example, if you want to solve the shortest path using dynamic programming, you can apply reinforcement learning techniques for doing that. Then heuristic and meta heuristics. So heuristics and meta heuristics are nothing but like someone gives you a problem and says that solve it within 5 minutes. I need a solution within 5 minutes. But he doesn't care about the quality of the solution. In those cases, someone can come up with a heuristics and give it. So heuristic is nothing but uh, not an immediate solution to a problem. That's it. And meta heuristics or something like given a solution, you will try to, like, let's say I am at a, for example, we can take the same how to say, the gradient descent problem. The gradient descent, we will have a hill, right? So usually that's how they represent. We'll have a hill with multiple valleys and multiple tops. So let's say we are at some point at the near the valley. So, and the heuristics has given us that this is a good solution. Then what we can do is we can apply meta heuristics. So meta heuristics, what it does is near the region, of the solution provided by the heuristics or some other algorithm, it will do the search. And if near the region, if some points give better results compared to the actual solution, then it will say that, okay, this actually improves our solution, so this is a better solution. So that's actually what meta heuristics does. Meta heuristic is nothing but a local search around the solution to find better solution. So with this basics, I think we can go to the vehicle routing problem. So, and actually what we are going to discuss is a constrained vehicle routing problem. So the constraint over here is given to the load, like capacity, how much load a vehicle can carry. So this is how we can define the CVRP. Given a fleet of vehicles with a limited capacity, a set of customers with known demands, and a depot, find the optimal routes for the vehicle to serve all the customers while minimizing the total distance traveled. So CVRP actually combines both the elements of routing and also the resource allocation. So if we want to break down the CVRP into components, this is how we can do it. Like the objective function is to minimize the total distance traveled. So the constraint is our vehicle capacity. Each customer served only once. We should not visit the customer location. We should not pass through the same location again and again. Third, all vehicles should start and should end at the depot. And the decision variables are which vehicle serves which customer in what order. So, as discussed earlier, given a solution to the vehicle routing problem, we can verify its feasibility and calculate its cost in polynomial time. However, finding an optimal solution becomes very increasingly difficult. The complexity increases exponentially as the problem grows. So giving an exact solution is not feasible at all times. So now we know how we can break it. In the next slide, I will show you like one of the techniques which we can apply to actually solve it, and that is like integer programming. So let's say we are trying to apply integer programming to solve the CVRP problem. So this is how we can apply. So the variables in our hand are x of I comma j is equal to 1 if the vehicle k travels from a node I to node j, 0 otherwise. So y of I comma k equal to 1 if a customer I is served by vehicle k, 0 otherwise. And the parameters are the distance between the nodes I and j, and q of I, the demand of customer I, and q is the total capacity of the each vehicle. And the objective function that we want to minimize is summation over ijk dij, that is the distance travel multiplied by x of ijk. X of ijk is the vehicle k traveling from node I to j. So this is the total distance travel. So from D to I, D of ij will give you, let's say, 20 kilometers. Whether if x of ij, if the kth vehicle does the ij route, then we will put 1 here. So 20 will be get added here. So basically, we want to total minimize the total distance travel by a vehicle, by the vehicles. So what are the constraints here? So the constraints here is each customer is visited exactly once. So summation over k, yak equals 1 for each customer I. And the vehicle capacity. So this is the QI is the demand at each location, and summation of the demand into multiplied by YAK. YAK is the customer. So the demand for each customer should be less. Summation of demands for the customer should be less than the Q. If it is not less than Q, then the vehicle will not be able to satisfy that service that load. Flow conservation. Flow conservation, x of I j k equals x of j k equals y of k. So basically, flow conservation, what it means is when a vehicle comes to a particular node ij, then it has to leave that node. So ji. So whatever is coming inside should leave the node. Whatever vehicle is coming inside a particular location should leave that location. That's flow conservation. So subtour elimination is nothing but you sometimes certain routes are possible without involving the depot itself, but we need the depot. So subtour elimination is a constraint that is added to ensure that the vehicle starts at a depot and returns back to the depot. So the binary constraints are that's what actually makes everything as an integer programming. We make sure that all the variables are between 0 and 1. So either if a vehicle travels from I to J, I give 1 or 0. Or if a customer is satisfied, served by the load, I will give 1, or if else, if not 0. Then. So this is how you can formulate a CVR P as an integer programming. So these are like few constraints. In our actual case, we have added much more constraints. So this, if you want to solve it, you can't on a large scale, you can't just write it on a pen and paper and you can't just solve it. It's impossible. So what we do is we make use of the optimization packages that are available. And one such package that which we used was called OR tools by Google. But before that, let me try to motivate you behind why do we even need to solve this VRP? Where it is even being used, and why? How does it affect the business? How does it impact the business? So mainly, vehicle routing has to be done because optimizing routes can significantly reduce the transportation costs. So including the fuel consumption and the vehicle maintenance, and also efficiency improvement. So better routing leads to more efficient use of resources, allowing businesses to serve more customers with the same fleet. And again, nowadays concern, the environmental concern, it has very less carbon footprint. Once we have an optimized route, then the carbon footprint is reduced. Then the customer satisfaction. So efficient routing leads to quicker, let's say, deliveries and stuff like that. And so customer is also satisfied. So competitive advantage. So companies that can that can optimize their vehicle routing has a very competitive edge over other companies that hasn't that's not capable of optimizing their routes, because uh, the cost reduction and all the other four factors will impact this. So usually vehicle routing is done by all big companies. For example, Amazon, Flipkart, any delivery companies that you take, they do this vehicle routing. So the application is like wide, and this is the motivation behind the application is this. So then, what are the challenges then? I mean, if it is like widely used, then why is not everyone trying to uh, come up with a solution, apply it, and use it by themselves? Why are they like outsourcing the problem to some others? The reason being, CVRP is it's not a very easy problem to solve. So computational complexity is NP hard. Like I didn't explain hard, but NP hard is like I have introduced the non-deterministic problems, non-deterministic polynomial time problems, right? So NP hard is one such variety. It's at least as hard as the hardest problem in NP. That's what means NP hard. So we don't want to worry about the terminologies. For now, it's a very difficult problem to solve. And the computational complexity grows exponentially with the problem size. For example, if there are n customers, there are like n factorial possible permutations for a single route itself. So it's not an easy problem to solve. And there are like multiple constraints involved. Vehicle capacity constraint, and sometimes the time window constraint is also involved. Let's say some orders have to be served like in a within a certain time duration. So then we need to include this time window as another constraint. So, and again, some other constraints can also come into picture. For example, humans can work only from morning 8 to 5. So that's again another human-based constraint which we can add. Or uh, let's say the refueling can be added as another constraint. Refueling has to be done at this particular location. So that constraints can be added. So many variety of constraints can be, we can just keep on adding to the existing problem itself. And the main thing was the interdependence of the decision. So let's say I am assigning a customer to one route affects the feasibility and the optimality of the other routes. Let's say I'm trying to service a customer in particular route using a certain vehicle. Let's say that vehicle can carry like 100 kgs. But in the another route also, if I need another 100 kg vehicle, then we might not have it. So we need to come up with an optimal way of even choosing the vehicles, like which vehicle can I assign to which location. And if I assign a vehicle to a particular location, then it actually affects the servicing of the other next location. So the interdependency also plays a big role in solving this. So finally, like I will walk you through the flow chart of how we came up with our method for solving solving our client's business problem. So basically, what we do is we get the orders and the vehicle list. So basically, the order list contains the depots. Depot can be like a certain central location or a warehouse from which the vehicles will take the load or carry the packages or stuff, and then they take it for delivery. So there are like multiple warehouses. So, and for each warehouses, there are like various location it can serve. So those details are present in the order. So, okay, order will contain the depots, the list of areas that the depots will serve, and the orders along with the orders for that each locations, along with their capacity, along with the load for each order. So that's present in the that will be present in our order file. And the vehicle file, what it contains is that it contains the list of vehicles along with their capacity, carrying capacity, and also the cost, the cost for hiring that vehicle. So given these two things, what we first do is we first filter and group the orders. So basically filter and grouping the order, the first step what we do is we have to remove the orders that which we can't serve. For example, we have all our vehicles, the maximum load that our vehicle can carry is let's say 1000 kg. But we have an order that is like 2000 kgs or 3000 kgs. We will not be able to service those orders. So first we will filter those things out. And then what we need to do is we need to group the orders. So grouping the orders is done based on a location. Let's for a particular pin code, there will be like multiple orders. So we need to group them. So that grouping is performed in this grouping operation. So once we have grouped the order, and once we have filtered the remaining, filtered out the orders which we can serve, then we will try to minimize and maximize the size of a cluster. So basically, what we do is like I already mentioned over here, the computational complexity is very high. It's NP hard, meaning it's very difficult to solve a problem when the number of customers that or the number of customers that you want to serve is high. So in order to reduce the breakdown this, what we do is we given a given the orders, we try to cluster those orders based on the location. So how do we choose the clusters? Is like from the depot, we will fix 50 kilometers. So anything that is above 50 kilometers will just get filtered out. And then now let's say we have some 1,000 orders and 1,000 orders with 100 different locations. Now what we do is we will try to cluster this 100 locations. So we can, let's say for that 100 location, we form 5 clusters. Then basically it means like all the nearby locations will be grouped together. That's what we are going to do. And for doing that, we need to, instead of like some person manually entering the number of clusters to be formed, what we do is we come up with a automatic way of doing it. So basically, we run the k-means clustering multiple times using different cluster sizes, and we plot the elbow plot, and we choose the optimum value for the cluster size using the elbow plot. So once the optimal number of clusters is fixed, then we need to let's say we have 5 clusters and we have 3 or 4 vehicles in our hand. Then how should we assign vehicles to this clusters for serving? So that's the next question. So then for doing that, we need to, let's say one cluster can have like a load of 1,000, but we will have vehicles only with a maximum carrying capacity of 500. Then for that particular cluster, we need 2 vehicles. Then the question is like, which 2 vehicles do you pick? For that, we from the vehicle list, we will be having the cost for picking a vehicle, cost for hiring a vehicle. So we need to make sure that we hire a correct, we choose the optimal number of vehicles that satisfy our requirements. So once the vehicles are chosen, we will do the vehicle routing for each cluster. So this is what we basically do. Now, if there is any question, I can answer. Otherwise, I will go to the code. Yeah, Sridhar. Yeah.
Yeah, just wanted to figure out if the criteria for costing is only the distance which is less than 50 kilometers and the location, or is it also based on the tonnage, the time of start, and your priority in which the vehicle should start?
No, no. Now
Are those
the
also other criteria, or is this the only two criteria that you've looked at the
no
clustering
only the
part of?
distance criteria only.
Okay, only the distance criteria
Yeah,
and the
yeah.
location also because you said location. So what if your
Hmm.
location, the route changes, the kilometer increases, etc. See if that hasn't been taken into account. If you have
No,
to have a
this
detour and all that stuff.
no, this is not a dynamic way of doing the vehicle routing. This is a static way.
Okay,
Like
got it.
this vehicle routing will be done in the warehouse and it will be given so that vehicles will know that I have to service this customer in this order. That's the only purpose for this vehicle routing.
Okay, so the priority with the customer served are also taken into account the booking time,
Yeah, yeah, that
etc.
can be
Or
added as a constraint.
that can
That's
be
what
added
that
in.
yeah, the time window constraint comes into picture, saying that certain customer has to be serviced in certain time window. That can be added as a constraint.
Okay, got it. Sure. Thanks, Sri.
Thank you.
Okay, any other questions? Okay, so I guess we'll stop it here.
Papa, don't need the code review. The code walkthrough.
Yeah,
But
you can
Sri,
do
is
that.
this something that has been, sorry, Arun, is this something that has been tested and we've given it to any customer, or is it,
Yeah, yeah, we have actually given it to our customer.
and what was the level of confidence which they sort of exhibited in this results that we got?
If you ask me, I have to say they were satisfied.
Okay, but only with those two constraints are satisfied and
No, Windows, no, no, no. That's what I'm saying. I just gave you a simple explanation in this PPT. I've added more constraints in the code.
oh, okay, got it, got it. So the
Okay, I
overall
mean,
satis
yeah, yeah, I've added time window constraints and also like optimizing the vehicle, picking the correct number of vehicles. Those sort of constraints, extra constraints I have added.
you've added it. Okay, got it. Good enough. Yeah, thanks, Sri. Sounds good.
So on the for your other question, like for if you want to do this dynamically or adaptively, if you want to do the vehicle routing, then reinforcement learning techniques have been applied. Like it's currently under research. I mean, there is. I won't say that. I can't say with certainty because there is there hasn't been any deep learning models capable of solving combinatorial optimization problems. Not yet. People are
Got it.
still researching on that.
Got it. Yeah.
So these are the current research areas for the for solving this vehicle routing problems. One is using graph neural networks, and the other is using quantum computing.
Wonderful. Got it. Yeah. Good.
Okay,
Thanks, Shri. I think that's good. Yeah, please go ahead.
just some fast walkthrough on the code. So basically, like I said, these are just the inputs, which forget about that. So the input file. So the input file contains the orders and their respective delivery locations, and also the DC. DC name is nothing but the depot. So once this is the input file, and the vehicle file is nothing but the vehicle list for a DC. So a particular certain set of vehicles are reserved for a DC. And only for the orders pertaining to that DC, we can only make use of these vehicles. So, and this contains the cost for the vehicle ID, stuff like that. So then first, then what we do is we group the shipments to same location as a list. So, so here, for example, list of orders that go to the same pin code will be grouped together. And then we will get the serviceable nodes. So we will, like I said, we'll be filtering out. We will filter out orders that are greater than 50 kilometers. We'll only focus on orders that are within 50 kilometers of a particular DC. And then getting the optimal K for the clustering the large number of orders. Uh, and then actual clustering takes place here. So basically what we do is we apply the K-means algorithm multiple times for different cluster numbers and then pick the best one. So
How
this
many
is
times did
the
you have to run it?
hmm,
How many times did you have to run it? Multiple times you said. So,
that's your choice. For
no,
here,
but
I
in our
think I am running it
practical,
for
this,
yeah. For here, I am running it for 3 times. I think
okay,
3 or 4.
got it.
So then we create what is called as a data model. Data model is nothing but will contain our clustered location. The for each location the orders and the number of clusters. So you just have to pass it to this is how the OR tools, the framework which we use for solving this problem expects this. So, and then here are for example, here is the optimal vehicle constraint which we are adding. So here we are adding one constraint. Uh, Either so the first thing is, this is either you choose a vehicle or you don't choose a vehicle. That's why it goes between 0 and 1. So that's the integer thing. And so what is your constraint? Constraint is the sum of the vehicle capacity should be greater than or equal to sum of the demands. So let's say for a particular cluster, the demand is like 800 kgs. Then we make use of a vehicle that is greater than 800 kgs. So that's on constraint. Similarly, like there are like constraints based on the vehicle cost. So the objective is to minimize the objective is to minimize the cost of the vehicle, and we have the list of the vehicles. So we use this constraint. So we make use of this constraint to solve this objective. For finding out the optimal vehicles. And then this is routing. So routing also we do like we'll first figure out what is the distance matrix or the distance between each nodes, and then we will try to just like how we how we mentioned in that PPT, like all the constraints are written down, and then we will apply a solver to solve that. So the solver is it's an analytic. We make use of a solver because, like I said, like uh, it's not easy to just write the solution in a pen and paper sort of thing. So we need to make use of an computer-based analytical solver to solve this problem. So once we so in our case, what we do is we first make use of the heuristics. So cheapest are heuristics to find a simple solution, and then we make use of the guided local search as a meta heuristics to improve our solution. So if a solution is found, it will return solution feasible route is found. If no solution is found, then it will say no feasible route is found. And then finally we extract the routes, and then we can, if you want to do bin packing, can do bin packing and finally do the give the results to the clients. So this is how the result looks like. For example, in this case, the center point is the depot, and there are like three vehicles serving three different clusters. Each in one color. And if you bin packing is nothing but you need to arrange the packages or the loads into a container in a optimal fashion. So let's not talk. This is also the same. Again, you need to apply you need to convert this into a mathematical framework. Come up with what is the objective function and what are the decision variables that you have, and what are the constraints you have. Then you have to apply a solver for solving it. So once you do everything, this is the output that you get.
Okay. Yeah, sounds good. Any questions?
I think I'm good.
Okay.
Thank you, Srihari.
Thank you, Sherry.
Any other questions, please? Yeah, Ganesh.